Okay, so to finish up the total correctness proof for this same algorithm, so in the last video I did the partial correctness, proving that it always guarantees the post condition. In previous videos, I've kind of explained why proving those three properties are the variant that it belongs to the set of natural numbers. That if it equals 0, that it terminates, and that it reduces every iteration. Why, if you can guarantee those three properties, then it proves that the loop will terminate. So now we're just going to try and come up with a variant, and then kind of prove those three properties. So first of all, the property that I always think about first of all is just what is always reducing and will equal 0. So like if a equals 0 here, the loop doesn't terminate. If y equals 0, the loop doesn't necessarily terminate. So what I might try here is like a times y. Sorry, a minus y. As just kind of just like a intuitive guess, because if a is equal to y, then a minus y will be 0. Because if a is equal to y, then a minus y is equal to a minus a, which is equal to 0. So therefore, if a minus y is equal to 0, then a is equal to y, in which case this loop terminates. So that's pretty much my variant explanations, at least at the moment. I'm going to ask one about this, but at the moment they include kind of like a lot of normal language sentences like that, just to, like proving it. So you can say that, you know, like if a minus y equals 0, then a minus y, the condition is b, therefore a equals y is the equivalent to not b, therefore if a minus y equals 0, the loop terminates, is just kind of like the logical explanation I go through for that. But we can all kind of see that if a minus y is equal to 0, that the loop will terminate. So there's our first property kind of explained. The second one is that it needs to belong to the set of natural numbers. So it's initialized to 0, and it only ever gets incremented by 1. So again, just kind of plain words description that a belongs to the set of natural numbers, and y here is stated as greater than or equal to 0. So therefore, if it's a natural number, or you could even kind of like list this as a precondition, because I guess does this loop work if y is equal to 1.5? And the answer is no, because it will skip past today. It will never equal y. This will go forever. And that's actually not listed as a precondition. It does still meet the requirement that's greater than 0. So you can actually just kind of like write on that you need to assume y is an integer, or something like that, because that is actually a requirement for this algorithm to work. But basically, if a is something in the set of natural numbers, and y is belongs to the set of natural numbers, then so a starts at 0 and y is greater than or equal to 0. Then what we actually get is that maybe this doesn't work, because let's say like y is 5, right? Well then 0 minus 5 gives us negative 5, which does not belong to the set of natural numbers. Negative numbers are not natural numbers. So that's kind of, whoops, we screwed our variant. But that's fine. So our proof that this was the variant, we're just trying to find out what our variant is, was wrong the first time around, but probably on the right track. So let's try y minus a instead, right? So this has the exact same proof for y when that equals 0, they're the same, because when y minus a equals 0, then y equals a, and when y equals a, the loop terminates. So we've got our exact same proof from before. Now we know that a equals 0 and y is greater than 0, so we know that y must be greater than or equal to a, and we know that they both belong to the set of natural numbers. And so from there we can kind of see that since a starts at 0, if y is also equal 0, then the loop terminates. Otherwise, y minus a, for any condition that would actually run through the loop, will always belong to the set of natural numbers. And again, I'm not sure if these kind of plain words descriptions are enough for the assignment. This is what I want to double check. but at the moment I'm just kind of logicking through it. And the final condition is just that, what have we done so far? We've done that when they equal 0 the loop terminates, we've done that they belong to the set of natural numbers, that it decreases every time. Okay, so yeah, here we've got, we would have run into the same issue here if we hadn't caught it earlier, but so if our variant is equal to y minus a, then every iteration we've got a plus 1, so if we kind of say, and I think the way they did it in one of their things was that here they've inserted almost an assertion that y minus a is equal to the original value of our variant, which they called like capital I, but I think that's because there was a little I. But let's just use it anyway. So y minus a is equal to capital I, whatever it happens to be. And then we've got z equals z plus x, that doesn't affect it. A equals a plus 1, which means y minus a plus 1 is no longer equal to I, but that is in fact greater than I. And that's just through kind of like basic math. You could substitute this back in, so y minus a plus 1 is greater than y minus a, because like math axioms, x is less than x plus 1 little shit. So this statement is true, and since this was the initial value and this is the like adjusted value, we know for certain that y minus a plus 1, nope, sorry, I forgot the brackets. When you substitute that in, it's y minus a plus 1, not y minus a plus 1, which means when you expand that, sorry, I've totally flipped this around the wrong way, we have y minus a minus 1, which will always be less than y minus a for the same reason. So we've proved that the new value will always be less than the original value, and thus we've proved that our variant y minus a is decreasing every iteration. So again, I'm not sure how formal all that needs to be, but that's kind of the general process you go through to prove the variant. And then between those two, the partial proof correctness and the proof that the variant satisfies those three conditions, you have the total correctness.